This video is all about determining the shapes of molecules. So you can see a whole bunch of different shapes here on this slide. So various different molecules, CO2, SO2, SO3, NF3, ClF3, they all have very different shapes. Linear, bent, trigonal planar, trigonal pyramidal, T-shaped. There's just some examples of the various different shapes that molecules can adopt. So this video is all about determining what will be the shape of a given molecule. Now up to now you've looked at Lewis structures, but that doesn't tell you, so Lewis structure tells you the bonding and lone pairs in a molecule, but it does not tell you the shape. But the Lewis structure can help you to get to the shape. So this is the Lewis structure of an imaginary molecule AB3. So you can see here that the Lewis structure's got various bonds and lone pairs drawn on it. But you need a new concept now, which is the concept of electron domains. So electron domains is like is a region of electron density. So consider atom A here, the central atom. So atom A has 4 regions of electron density around it. This bond here is a region of electron density. This lone pair is a region of electron density. This bond is a region of electron density. And this double bond is 1 region of electron density. So there are 4 regions of electron density, 4 electron domains around the central atom. And it's this concept of electron domains that allows you to move from a Lewis structure into the true shape of the molecule. And to do that, you just need a theory called valence shell electron pair repulsion theory, VSEPR theory. It's a very fancy name for a very simple concept. Basically, VSEPR theory just says the best arrangement of a given number of electron domains is the one that minimizes repulsions. So you can basically just think about balloons. So imagine that you've got an atom here, a little clip in between 2 balloons, where a balloon represents a region of electron density. If you have 2 balloons, then they will naturally spring into this kind of linear orientation in order to get as far away from one another as possible. If you have a molecule with 3 regions of electron density, then those will prefer to adopt a trigonal planar arrangement to get those 3 balloons as far away from each other as possible. If you have 4 regions of electron density, they'll prefer to go into this tetrahedral arrangement. So today we're just going to look at different patterns here, going from 2 to 6 electron domains and the various different shapes that can be adopted, going from linear, trigonal planar, tetrahedral, trigonal bipyramidal, and finally octahedral. So let's start looking at some of these one at a time. This is actually how you go through the process of figuring out what is the geometry of the molecule. So the example here is from ammonia, NH3. You now know how to draw the Lewis structure. After you draw the Lewis structure, you count the electron domains around the central atom. So in this case, the nitrogen is surrounded by 1, 2, 3, 4 electron domains, regions of electron density. So you know that that nitrogen is going to have a tetrahedral arrangement of those regions of electron density. So the nitrogen atom will have a tetrahedral shape with a lone pair at one vertex and hydrogen atoms at the other 3 vertices. And finally, to quote the overall shape of the molecule, the important thing to remember is we don't include lone pairs when we're talking about the shape of the molecule. We only talk about the locations of the atoms. So in this case, the locations of the atoms make a trigonal pyramidal arrangement. So we would say the shape of the molecule is trigonal pyramidal. That's a key point. You don't include lone pairs when you're talking about the shape of a molecule. Okay, so let's go through these different numbers of electron domains one at a time. If you have 2 electron domains, the electron domains will be arranged in a linear arrangement, and all the examples you're going to see, they will both be bonding domains. You won't have any non-bonding domains, and so the molecule will adopt a linear shape. And so an example of that would be CO2. That's the simplest case. Now if you have a trigonal planar electron domain, so if you have 3 electron domains, the geometry of the electron domains will be trigonal planar, but you can get different molecular geometries depending on whether these are all bonding or some of them are non-bonding. So for example, if all 3 of them are bonding, then you're going to get a trigonal planar molecule. An example of that would be BF3. Whereas if you've got 2 bonding domains and 1 non-bonding domain, then you're going to get a bent molecule, and an example of that would be NO2-. This is what it looks like, the possibilities for if you have a tetrahedral electron domain geometry, so 4 regions of electron density. If they're all bonding, then you're going to get a tetrahedral molecule, such as CH4. If you have 3 bonding, 1 non-bonding, then you get a trigonal pyramidal molecule like NH3, which is the one we've already discussed. If you have two bonding, two non-bonding, you're going to get a bent molecule, for example, H2O. Okay, so we need to look into a little bit more detail now about the subtleties of bonding versus non-bonding electron pairs. So imagine this is a depiction of a bonding electron pair between two nuclei, and this is a depiction of a non-bonding pair, so it's just one atom with a lone pair. So you can see that the lone pair is actually bigger, has a larger steric demand than a bonding pair. And that's reflected in the geometry. So if you have a molecule like methane with 4 bonding pairs, then you have a perfect tetrahedral angle here, 109.5 degrees. In ammonia, with this big old lone pair sitting up here, that's actually got a large steric demand, and it pushes all the hydrogens down, and you see this bond angle is compressed to 107 degrees. And even water with 2 non-bonding pairs, then those bonding pairs, the OH bonds get squished even down closer to each other. This angle is compressed to 104.5. Another subtlety you need to know about is the steric demand of a multiple bond versus a single bond. So if you have a multiple bond, such as a CO double bond, a multiple bond is larger and has a larger steric impact than a single bond. So this is a trigonal planar molecule, but it's not perfectly trigonal planar. The bond angles are not 120 degrees exactly, because you've got a multiple bond here, that's a larger steric demand. It's going to widen this angle here to 124 and compress this angle down here to 111. Okay, so everything we've looked at so far, all the molecules on the slide so far have obeyed the octet rule. But you know that if you've got an element that's in row 3 or higher, then you know that it can make more than 4 bonds, and so that means we're going to have more shapes possible. So let's have a look at see what happens when you have more than 4 bonds to one atom. So here's an example where you have an atom in the middle that's making 5 bonds. If that or 5 regions of electron density, and if that happens, they will be arranged in this trigonal pyramidal shape. And this shape is a bit unique because it's got two different types of distinct positions. It's got the axial positions here, top and bottom, and it's got the equatorial positions, 3 of them around the equator around here. So here's an example of molecules that have trigonal pyramidal arrangement of electron domains. So once again, there's different possibilities depending on whether they're bonding or non-bonding. If they're all bonding, then your molecule will be trigonal bipyramidal, like PCl5. If you have 4 bonding, 1 non-bonding, then you're going to get this geometry here, which is it's called a seesaw. So if you imagine, if you really look carefully, you can imagine that these would be the feet of the seesaw, and this would be the bits that children sit on and go up and down. You've got to really squint to see the seesaw picture. If you've got 3 bonding domains and 2 non-bonding domains, then you get a T-shaped molecule. If you have 2 bonding domains and 3 non-bonding domains, then you're going to get a linear molecule. An example of that would be xenon difluoride. Now, there's a bit of a subtlety here because you imagine this case here when you go 4 bonding domains, 1 non-bonding domain, you can have 1 lone pair, and that lone pair could either be at the axial position or the equatorial position. Notice here that the lone pair has gone to an equatorial position in all cases. The lone pairs prefer to go to equatorial positions. And that's because there's actually a bit more room around these equatorial positions than there is around the axial positions. So that's something that you need to know. Lone pairs in a trigonal bipyramidal geometry, lone pairs prefer to go in equatorial positions. Okay, so let's look now at the octahedral geometry. So if you've got 6 regions of electron density, they're going to form an octahedral geometry. If they're all bonding pairs of electrons, then you're going to get a molecule that has an octahedral geometry, like SF6. If you have 5 bonding, 1 non-bonding, then you're going to get a square pyramidal molecule, and that's an example of that would be BRF5. And you notice here that it doesn't matter which position the lone pair goes on, because all of these 6 positions are equivalent. Now finally, if you've got 4 bonding domains, 2 non-bonding domains, then you're going to get this square planar molecule. An example of that would be xenon tetrafluoride. So they're all the shapes of molecules that you need to know about. If you go to a larger molecules where we've got more atoms in them, it no longer really makes sense to give one label in terms of shape to the entire molecule. So it makes more sense to look at individual atoms and consider the geometry of individual atoms rather than the geometry of the molecule as a whole. So in this molecule here, acetic acid, or vinegar, you can see here that it doesn't make much sense to talk about the overall shape of the entire molecule because it's getting a complicated shape. It makes more sense to talk about this carbon atom is tetrahedral, this carbon atom is trigonal planar, this oxygen atom has a well, the arrangement of electron regions of electron density around the oxygen is tetrahedral, and the molecule is bent in this position. So it makes more sense just to talk about individual atoms within a more complicated molecule. Okay, finally, you need to be able to predict whether a molecule will be polar or non-polar. So first of all, you need to work out whether the individual bond is going to be polar or not, and you do that by comparing the electronegativities of the two atoms involved in the bond. So in CO2, for example, it's got two carbon-oxygen bonds. They will both be polarized. But because of the geometry of the CO2 molecule, which you now know how to figure out, because of the geometry, those two dipoles are exactly opposite each other. So they cancel each other out, and overall this is a non-polar molecule. In contrast, let's look at the water molecule. That's got two OH bonds. Once again, because of the electronegativity difference, both of these bonds are polar, but because of the geometry of the molecule, these bonds are not, the molecule doesn't have that level of symmetry, so the dipoles altogether will sum to give an overall dipole moment for the overall molecule. So the water molecule is polar. That's it. I'll see you in class. Thanks.